Hello, everyone. Just want to thank you so much for coming to the JUMP Winter Test Prep Zoom session tonight. Um, your study consultant will be Angel, and she'll be walking you through, I believe it is the foundational chemistry building block and functional group session tonight. So if you have any questions or technical issues, feel free to message the JUMP um, correspondence or my name tag. My name's Amanda, and other than that, y'all enjoy. Thank you.
Hey guys, um, I'll probably give it just about one more minute for people to finish trickling in. So we'll get started at like 7:02 on the dot. Okay. Can everyone see that okay? So make sure I have the chat opened. Okay. Okay, so today we're going to be going over foundational subjects, foundational chemistry functional groups, specifically all of the high yield ones that you can expect to see on the MCAT, on your exam, most likely in your chem phys and biochem sections. So what we'll cover today. So today we're going to go over pretty much like all of the functional groups that are really important for you to know. So we'll talk about alcohols and phenols, we'll talk about aldehydes and ketones, carboxylic acids and carboxylic acid derivatives. And then we'll finish up with nitrogenous and sulfuric compounds. And to the side here, you can see what some of these look like. There is some carboxylic acid, a carboxylate, ester, amide, thioester, and if none of these sound familiar or make sense, that's perfectly okay. By the end of this lesson, you'll know them like the back of your hand. Okay. So first things first, I want to go over functional group priority ranking. So this is just a quick diagram of what like the actual IUPAC ranking for functional groups. So when you're going through nomenclature and um you're naming organic compounds, depending on the priority of the substituent, that's going to determine the name that pretty much the suffix that it'll take. So the suffix of every single organic compound is going to take, it'll take the suffix of the substituent that has the highest priority ranking. So like if we have a double bond and just a double bond, it'll be a pentene. All the time, your carboxylic acids are going to take the priority ranking. So this is going from like top to bottom. Alkyl is the bottom. And at the very top is carboxylic acids. If you ever see a carboxylic acid, just know that it's going to end in oic acid or carboxylic acid. Okay, now moving into alcohols and phenols. So we'll kind of first readdressing this diagram. Alcohol's pretty low on our priority ranking, but definitely still not the absolute lowest. So sometimes they will take the suffix of that. Okay, starting off with nomenclature. For alcohols, alcohols typically end with in OL. As for nomenclature, typically anytime you see any type of alcohol, you'll be able to identify it by that OL at suffix, especially like ethanol here or methanol, butanol. You typically have that OL suffix. A key identifiable feature is going to be this hydroxyl or OH group. That's going to signify to you that there's an alcohol in there. Also, when it comes to naming alcohols, it also depends on priority. So if it's our highest priority, that's when we'll have the suffix. If it's not, then we'll take the prefix hydroxy. So for example, we have here that for hydroxy 2-butanone, that's going to have a ketone group in it. So that's going, since that has a higher priority, it'll take the own suffix and that alcohol group will become in hydroxy instead. And this would look something like that. And then also depends on number of hydroxyl groups. So if you have 2 or 3, you'll have a diol. With a 3, you'll have triol. For tetrol, typically don't see it higher than that, but it can keep going, like a pentol, heptol, octol. It's just going to take the prefix for the number and then add all to it. Okay, general properties for alcohols. So this is something that we can kind of go back and forth with, or actually how familiar with alcohols and alcohol like chemistry is everybody on a scale of 1 to 10? 10 being, I know every little thing about it. 1, I'd prefer you just tell me everything about it because I know nothing. Okay, I see some 7s. I see a 9. See a 2, 7. Okay. Okay. It's kind of a mix, but we do have some people who are above 5. So we can kind of work together on this. So for solubility and melting / boiling point trends, getting into those colligative properties, can anyone tell me what the effect of what the effect on solubility that the addition of an alcohol group will have? You can either unmute or drop it in the chat. Will it increase it? Will it decrease it? Okay, I see in direct message to me, increase, and then in the chat, everyone to increase. Thank you. Exactly. It will increase it. Can anyone tell me why it would likely increase the solubility? please for these, like just say them to everyone just so that like we can all like see the answers. Exactly, Ryan, because of the hydrogen bonding. So as you know, oh, sorry. As you all know, hydrogen bonding is fun. So hydrogen bonding can occur between fluorine, oxygen, and nitrogen. Hydrogen bonding is a very strong type of bond. And also, when it comes to solubility, when we're thinking of things that are going to be soluble, especially like aqueous solubility, we know that polarity, hydrogen bonds, things that will make things more like water are going to be more soluble in water. So these will be very soluble in water. Alcohols will increase solubility. What about melting and boiling points? How is the addition of an alcohol group going to affect that? Any thoughts on that? Okay, yes, I see it in the chat. Increase boiling point. Yes, they are exactly going to do that. They're going to increase boiling and melting points. You can think of it as just remembering your colligative properties, specifically your freezing point depression and boiling point elevation. Whenever you have an increase in the strength of the intermolecular forces between atoms, you're going to have freezing point depression and boiling point elevation simultaneously. So with hydrogen bonds, that's going to be a very strong, those have very strong intermolecular interactions. Those hydroxyl groups, that hydrogen bond is very strong. And therefore, in order to break those bonds, you're going to need a higher temperature, or to kind of like push them together, you're going to need a lower one. Okay. Does that all make sense? So it'll be kind of just like, best way to think about it is as you have more and more hydroxyl groups, you'll have greater solubility, a greater higher boiling point, lower freezing point. Boiling and melting tend to go hand in hand since they're similar phase transitions. And okay. For acid-base chemistry of alcohols, can anyone tell me, are alcohols acids, bases? And with that, do we know if they're strong acids or weak acids? Weak acids, exactly. So acids, I mean, alcohols are weakly acidic. Um, and that acidity can change depending on if there's an electron withdrawing group or an electron donating group. Between the two, do we know which one would increase acidity versus decrease acidity? Or are we sure of what contributes to a weak versus strong acid in the first place? Like what makes something a weak acid? So we talked about how intermolecular forces and um, polarity are what's going to affect colligative properties and solubility, respectively. But what about acidity? What would affect acidity and alkalinity, I guess, hand in hand? Or you could put a thumbs down reaction if we don't know. So yes, kind of dissociation. So largely what's going to make something a strong acid or base will be based off of how if it fully or partially dissociates. By definition. But what will determine this, like what will determine if it will fully or partially dissociate, is going to be largely based off of the stability of the conjugate. And that conjugate can be the conjugate base or the conjugate acid. An acid will have a conjugate base. A base will have a conjugate acid. The more stable that conjugate base is, the more acidic, the more acidic that compound will be. So the more stable it will be after releasing that proton, the stronger acid it will be, because the more freely it will dissociate, the more freely it will let go of that proton. Just kind of thinking whenever you're dealing with like chemistry or organic chemistry, largely what things are almost always going to come back to is going to be stability and intermolecular forces. Anytime you're trying to figure out, okay, why is this happening? One of the first things you should think about is stability, intermolecular forces. Okay. And the alkoxides are just the name of the conjugate base for an alcohol. So a deprotonated um, ethanol will be this. I think it will exactly be pronounced ethoxide. Okay, so moving on to phenols. Is everyone clear on alcohols? Are we good to move on to phenols? Does anything need more explanation? Thumbs up, move on. Thumbs down. Go back and explain something. Okay. Did you explain the electron with drawing effect? Yes. Is there anything specifically you want me to explain about the electron withdrawing effect, or just
I was just
general?
curious, which, like what the effect of electron withdrawing and electron donating groups are on acidity.
Okay. Yes. So donating groups are going to destabilize our conjugate base. So they'll decrease acidity, versus withdrawing groups will stabilize our conjugate base. So they'll increase.
Okay, that makes sense. Thanks.
Okay. Phenols. So phenols are going to be alcohols with a benzene ring. The IUPAC nomenclature is largely going to be determined based off of the ortho, para, or meta locations of the substituent to the alcohol. So an example would be that this compound right here would be called, since this compound is ortho, this NO2 group is ortho to our hydroxyl group. We'd have O dash nitrophenol. Or ortho nitrophenol. General properties of phenols is that they are just like acids. They are also weakly acidic, but they are more than the than alcohols because of the aromatic ring. Again, can anyone like quickly drop in the chat why they might be more, like why the aromatic ring might contribute to increasing the acidity of phenols? What does aroma resonance? Exactly. So one of the biggest things in orgo is resonance and its effect on stability. Resonance greatly increases stability, and with our benzene ring, we have a series of 6 conjugated pi bonds that are in resonance, and therefore that kind of lone charge is displaced, as you can see in our 1, 2, 3, 4, 5 resonance structures. So it's not shared on any one single thing. And it's allowing for electron delocalization, and that is known as resonance. So phenols can also be oxidized into quinones. They are largely important in metabolism. In metabolic processes, quinones tend to come up a lot, specifically a compound called coenzyme Q. That's when you'll see a lot. Those are known as ubiquinones. Specifically, those are going to be, so as you can see down here, our quinones are going to have two hydroxyl groups that will be oxidized into two ketone groups. Okay, and this is ubiquinone. So that is also known as coenzyme Q. It's very important in the electron transport chain. It can carry 1 or 2 electrons. And those are the names it has when it's carrying the electrons. Okay, first question. I'll say just drop in the chat, either PM me if you don't want everyone to see, or say it to everyone. If you know, can anyone identify which compound has the alcohol? Give it like 10 more seconds for the answers to roll in. 7, 6, 5, 4. Okay. Okay. Most answers are in, and most people said C, which is correct. And not to be tricked by B, because although it does have that OH group, it also has this double bond here. And this CO double bond, this is known as a carbonyl. When we talk about ketones, we'll explain it more. But when you have a carbonyl with one of these substituents being an OH group, this kind of OHCO double bond group, this is known as a carboxylic acid. Okay. Okay, another quick question. How would the boiling points of the 4 compounds shown rank from least to greatest? Once again, either say it to everyone or PM me, either one works. Guys, maybe a minute for this one. Okay, I'll give it 30 more seconds. Actually, sorry guys, I just realized something. In the answer choices, I switched these. So this should be 2 and this should be 1. Instead. So feel free to resend based off that. I'll start going over it in about 10 seconds. Sorry about that. Okay. We'll start going over this. So for this one, the answer is I had a mix of answer choices, but the majority was B, I believe, which is correct with this arrangement. So we can tell that this is going to be the least because this is the only one with no aromatic ring. And on the MCAT, if you have something where you're like, oh, I already know that one's going to be at the bottom, then you can pick that one and keep going. But for the sake of making sure it's understood, I'll go through each one. So this has no aromatic ring. So it'll have the lowest stability compared to everything else. And the next reason why we go 4, 3, and then end at 2 is largely going to be because we have these polar charges here for 3 and 4. That will be actually lowering the boiling point compared to 2. Does that all make sense? Wouldn't the ionic bonds increase the boiling point? That would be, it's actually the opposite. So the ionization is going to decrease the boiling point, at least compared to 2, because this is going to be largely the most stable structure that we have. And that's why it's going to have the highest boiling point. So breaking those bonds will be the absolute hardest for something like 2, which has like aromaticity and a hydrogen bonding as well. So our solid OH group versus 4 and 3 are going to largely be significantly more unstable because of those charges. So they're going to be a lot more, it'll be a lot easier to break those bonds, meaning that the boiling points will be lower. Does That makes sense? Okay. Okay, moving on to aldehydes and ketones. So, quick introduction. These are example of some common aldehydes, some common ketones. If you look, you can kind of already see some common things in terms of the naming. You can see some common suffixes and prefixes. But largely, it's going to be most important is we have the introduction of this carbonyl. So nomenclature always depends on priority. Before you name anything, think about the priority. For aldehydes, the suffix will be al. So propan, al, propanol. Or plus carbaldehyde when attached to a cyclic structure. So an example was cyclohexane carbaldehyde, which would look like that. Ketones, their suffix is going to be -one. And then when they're not the highest priority, they're going to have this oxo prefix. So a quick exercise I have is, based off of that, can anyone name the compound that we have to the right? Oxopentanone is very, very close. So oxopentanone is right almost there, but so whenever you have a structure like this, where you don't have another bond next to it, you can always assume that the empty bonds, when drawn out like this, are hydrogens. So because we have a carbonyl bound to a hydrogen, that's going to be an aldehyde. When we have a carbonyl bind to two R groups and one is not a hydrogen, that's when we have a ketone. So this will be an oxopentanal. And then also, whenever you're naming compounds, just make sure you also include the number. So you have 1, 2, 3, 4. So it'll be 4-oxopentanal, just so people know where that other where the ketone is. So does aldehyde always take priority over ketone? Yes. Priority rules are set in stone. Can we also say 1-oxo-4-pentanal? No, that's not, you can say that and people will be able to figure out what you're, actually no, because this is also a ketone. So our oxo is standing for our ketone. So if you wanted to say that, you would have to change the name entirely. Like 1-oxo-4-pentanal would not be the name for it. Physical properties. So for some physical properties of aldehydes and ketones, our carbonyl is going to be polar with no protons, so a polar aprotic model. Oh, quick question. What would they be considered in acid base under what convention? So by conventions, I mean like Lewis, Bronsted, Lowry. And Arrhenius. Would they be a Lewis acid base, Bronsted Lowry acid base, and Arrhenius acid base? Or an Arrhenius acid base? You can either unmute or drop it in the chat. Let's see. A Lewis base. Or maybe does everyone know what the difference between a Lewis, Bronsted, and Arrhenius acid and base are? Oh, okay. Does anyone want to drop it in the chat, or I'll just quickly go through it. So Bronsted, Lowry, and acid will donate. Yes, Lewis is about electrons. This is about protons. And this is going to be about our protons plus OH, or our hydronium. H3O plus ions. So this will be only Lewis, mainly because like the key thing to recognize that was going to be the polar aprotic model. So since these are going to be polar aprotic, that means we have no proton. And Bronsted, Lowry, and Arrhenius both require protons in order to be categorized under either of them. So just keep that in mind, because that's a common, easy, discrete question that they tend to ask. Is this a Lewis or Arrhenius or Bronsted Lowry base? Okay, so effect on melting / boiling points. keep in mind our carbonyl and our double bond. Just drop it in the chat. What likely might it be? Our double bond is stronger than a single bond. Okay. So it will increase. Yeah, thank you. Someone get me. It will increase them because of that double bond. But again, polar aprotic, that in mind. So we don't have our hydrogen bonding, and hydrogen bonding is going to be our strongest type of intermolecular force. And therefore, it won't be as high as, for example, our alcohols or carboxylic acids, but it will be higher than an alkane, for example. Another big thing is acid-base chemistry, and of importance to think about is like our alpha, beta, etc. carbons. So from each distance from our carbonyl, that's how we start counting alpha, beta carbons. They typically have alpha hydrogens that are weakly acidic. But they do also still have resonance stability. Okay. Then lastly, just remember that aldehydes are slightly more acidic than ketones. Okay, quick practice question. How would you rank the compounds shown below in terms of acidity from least acidic to most acidic? Either PM me or drop it in the chat. A quick like understanding check. I'll give it about 30 more seconds. Think about the effect of electron drawing groups. Okay. We're just about done. And for the most part, it seems like the most common answer I received was D, which is exactly correct. So biggest thing here is that you always want to think about the stability of your conjugate base, and between 3 and 2, mostly because Cl is a larger ion than fluorine. And we also have this is going to contribute to the increase in acidity with fluorine. And this also is a ketone, which will both be less acidic than our aldehyde. Okay, for this one, I would say maybe just tell me this one. For this carbon, would it be an alpha, beta, or gamma carbon? Yes, gamma, exactly. So you just count the distance from the carbonyl specifically. Since we're 1, 2, 3, you go alpha, beta, gamma. And it just follows the Greek alphabet. Okay, now into carboxylic acid and carboxylic acid derivatives. So carboxylic acids are the highest priority functional group, as we saw in our table. So compounds will always take their suffix, which is largely going to be oic acid. So typically, so a good example would be like if you have ethanoic acid. There's also known as, also have acetic acid, methanoic acid. Very easy like that. And then for cyclic compounds, they'll have the name carboxylic acid. So cyclohexane carboxylic acid, just like how we had cyclohexane carbaldehyde. And acetic acid and formic acid are testable. So just kind of keep that in mind, that acetic acid is ethanoic acid, vitamin C, and methanoic acid is formic acid. Physical properties. Okay, so what kind of intermolecular interactions do you see between carboxylic acids? Starts with an R. And H. We see resonance. We see resonance and we see something that starts with an H. Hydrogen bonding. Exactly. Both things that will greatly increase the acidity. Carboxylic acids are all extremely strong, very strong acids. And how would this likely affect melting / boiling points? So we've been going over it. Would it increase them? Would it decrease them? It'll increase. So the addition of a carboxylic acid group will largely increase the boiling point. Okay. For acidity, just remember that the most acidic hydrogen is going to be that H specifically, and not like if you had a CH3, not this one, not any of those. This one would be much stronger. Okay, and there is also an inductive effect that you should take note of, but just remember that it decreases with the distance from the carbon. So resonance generally tends to have a greater effect than induction. And then here are some examples of some effects on substituents, the addition of substituents on carboxylic acid acidity. So we can see here when we have, as we add more electron withdrawing regions, we're going to increase our acidity. And as we kind of decrease stability, we're going to also increase, as we increase stability, we're also going to increase acidity over here. Okay, for carboxylic acid derivatives, you have about 5 of them. You have acyl halides, anhydrides, esters, amides, nitriles. We don't see as common, but mostly it's going to be these 4 that are testable. So acyl halides are essentially going to look like carboxylic acids, but instead of a hydroxyl, we're going to have a halogen group. These actually have low melting / boiling points, or lower compared to carboxylic acids. Can you tell me why? What did we change that reduced them? It's actually on the slide. Hydrogen bonding, yes. We got rid of our hydrogen bonding, which reduced our intermolecular interactions, which in turn is going to reduce that very high melting and boiling point that carboxylic acids have. And these are highly reactive. They're very, very, very reactive. And you typically see that when you have reactions where you want to go from a carboxylic acid to a ketone, for example, you often have this kind of acyl halide substitution come into play, where we have like Socyl, I call it Socyl and Pibber, or SOCl2 and PBr3. Those are common things like you see in organic chemistry reactions where you take a carboxylic acid into an acyl halide. Okay. Acid and hydrides. So acid anhydrides, these are carboxylic acid derivatives that are formed actually by a reaction between 2 carboxylic acids, generally. And they're joined with, you have an O, it's kind of like an ether with carbonyls, is how I like to think of it. Like almost like a marriage between ethers and carbonyls, because the form general takes. But typically you can identify it by just seeing this 2 carbonyl connected by this oxygen group, and it's generally joined, or their formation is largely a nucleophilic substitution reaction. For nomenclature, it depends on symmetry. So, and by symmetry, I just mean the way that your R groups are going to look. So if you have like a methyl group on each side for an R group, then you could call it methanoic or methanoic anhydride and leave it at that. Or if you have it asymmetrically, or let's say you have a methyl group and an ethyl group, then you'll go in alphabetical order. So you'll have ethanoic, methanoic, anhydride. Cyclic anhydrides, those are like extremely low yield. I would say I wouldn't put a lot of energy into committing them to memory. In less like you have extra time. Most likely, if there's a time where you need to know that, then they'll include it on they'll include it in the passage. It's unlikely that it'll be a discrete question where you need to know that. Esters, these are going to be carboxylic acids, but instead of a hydroxyl, you have kind of like an ether. So you have an OR group. And they tend to have an O8 suffix. So if you think about the conjugate base for carboxylic acids, it's typically O8, and that's very similar for esters. They'll have an O8 suffix. And another thing that we see with like cyclic esters, those are known as lactones, and they're named based off of the alpha, based off of the carbon. So if you have an alpha carbon, then it'll be in alpha lactone if you have a beta carbon. So the last type of carbon that you have, if you have a gamma, then it'll be a gamma lactone. If you have a delta, then it'll be a delta lactone. These also have lower melting/boiling points compared to carboxylic acids because, again, we got rid of our hydrogen group. They generally don't engage in acid-base chemistry and, once again, also can't hydrogen bond. So for naming esters, they're named based off of the carboxylic acid and alcohol that they're derived from. And here are some examples. So we have here methyl ethanoate because our carboxylic acid was ethanoic acid and our alcohol was a methanol. So we're just committed to memory that you're always going to go alcohol and then carboxylic acid whenever you're naming esters. Oh, we're kind of at time. So would you guys want to skip to nitrogen and sulfur compounds, keep going over carboxylic acid derivatives, or I can share the PowerPoint and close out? Share the PowerPoint. Okay. I will attach the PowerPoint here. I think there were 2 more little practice questions in at the end. But okay, so I put the rest of the PowerPoint in the chat. Are there any last minute questions or things that you guys would? Yes, I'll also post the remaining content packs or the packets for the organ systems I'll post everything in Canvas. Other than that, are there any other last minute questions or things that you guys want me to go over more about? This was just going to say more about the amides, how to name them, and then talk about common nitrogen and sulfur compounds. Possible to absolutely. I would say if there's any time that I'm going over something and you guys completely understand it, or if you're like, oh, we don't need to go over that, just say, oh, I get it. Or drop a 6 in the chat and we'll move on to the next thing. Any other questions? Any other thoughts? So yeah, this what is going to talk. The rest, you'll see more about reactivity and important compounds. That's all. Okay. Any other questions? If not, I'll see you guys on Tuesday, I believe.